Okay, so we've been looking at Cauchy. Sigma a squared, sigma b squared, greater than or equal to sigma ab all squared. I'm going to consider when equality holds. And you'll remember, so I'm looking at finding a and b, which are of course sequences, such that sigma a squared, sigma b squared, greater than or equal to sigma ab squared, not greater than or equal to, is actually equal to. Well, you'll remember in the proof we looked at sigma over I, sigma over j, ai bj minus aj bi squared, and we observed that that was greater than or equal to 0. So for equality in Cauchy, we need sigma over I, sigma over j, ai bj minus aj bi squared equals 0. So if I want to make this inequality an equality, we have to have exactly 0 in this term here. I'm going to assume that all the AI's are not equal to 0, and in fact I'm going to assume that all the BJ's are not equal to 0 as well, because if they're equal to 0 they wouldn't contribute to either side of the inequality, so we may as well just bin them. So what that says, what this equality says, is that the whole sum of squares is equal to 0. So what that says is that each term must be equal to 0 exactly, because if even one term was non-zero in here, it would be every term is non-negative, and so every term must be exactly equal to 0, because if even one term was a tiny bit positive, it would make the whole sum positive, because there's no negative numbers to cancel that out anyway. So that says that aibj minus ajbi equals 0 for every pair of I and j. So that says that aibj equals ajbi, which further tells me that ai over bi equals aj over bj, because I'm excluding 0 terms, every I and j, and the only way to do that, of course, so that must be a constant, which I'm going to call lambda. So that says that ai equals lambda bi for every I. So the only way to get equality, you remember we've got rid of the zeros, is for bi equals lambda ai for every I. So A and B are proportional. And of course the statement will just verify that it works. Sigma a squared, sigma b squared, greater than or equal to sigma ab squared. If we substitute b equals lambda a, we've got sigma a squared, sigma lambda squared b squared is greater than or equals sigma a times lambda a squared. We've got, sorry, that's a lambda, that should be an a squared. So we've got sigma a squared times lambda squared sigma a squared greater than or equal to lambda squared sigma a squared. Squared. And of course that's true because the two sides are the same. Equals lambda squared sigma a squared squared. And so we've got an if and only if statement. If we exclude 0 values, then a and b, if they're proportional, results in Cauchy's inequality being an equality. And if Cauchy's inequality is an equality, then a and b must be proportional to one another. Okay, I'm going to stop there.